Today, we're going to pull back the curtain on robotics and look at the skeleton that makes it all work. The fundamental rules that let a giant, powerful industrial arm move with the grace and precision of a surgeon. Let's get into it.
So think about it. You see a robot doing something incredible, like painting a car door perfectly. But how do we actually tell that robot's spray gun to get to a very specific point in space? And maybe more importantly, how does the robot translate our command, our go here, into the specific whirring of its own motors? That is the fundamental question of robot kinematics.
So here's how we're going to break it all down. We'll start with the robot's basic body parts, its skeleton. Then we'll learn the two different languages it speaks. After that, we'll figure out how to find its tool, and then how to put that tool to work. We'll even get into controlling its speed with something called the Jacobian. And finally, we'll talk about the danger zones every robot has to avoid.
Okay, first things first. Before we can talk about any kind of fancy movement, we have to understand what the robot is actually made of. And you know what? It's a lot like us. It all starts with a skeleton of bones and joints, or in robot terms, links and joints.
This is what we call a robot manipulator, or maybe a bit more technically, a kinematic chain. And this model is the foundation for pretty much every robot arm you've ever seen. Now, the key assumption here is that the links are perfectly rigid. They don't bend, they don't stretch, and that one little assumption makes the math so much easier, letting us focus only on what's happening at the joints.
And here's the wild part. Almost every single complex robotic motion you can think of is just a combination of these two super simple joint types. You've got a revolute joint, which just rotates, think of your elbow, and you've got a prismatic joint, which just slides into straight line, kind of like a telescope. You put them together in a chain, and suddenly you can create incredibly complex movements.
And this brings us to what is, maybe, the most important concept to get your head around in all of robotics. We humans, we think in what's called Cartesian space. We tell the robot, hey, go to these X, Y, Z coordinates. But the robot, it only understands joint space. It only understands commands like rotate joint 1 30 degrees. The entire game of robot control is about being a good translator between these two languages.
And that translation happens on what we can call the kinematics bridge. Now, going from the robot's language to ours, that's forward kinematics. It is the easy direction. But going the other way, translating our simple go here command into the exact motor angles the robot needs, that's inverse kinematics. And that, my friends, is where things get really, really hard.
So we know the parts, and we know there are two different languages. Now let's look at the actual grammar that connects them. How do we use math to precisely describe a single part of the robot rotating and moving through 3D space?
The solution is just, well, it's elegant. Instead of trying to juggle separate equations for where something is and how it's rotated, roboticists combine everything into one powerful tool, a single 4x4 matrix. This is the absolute secret sauce. It lets us describe a complex move like rotate a bit, then move forward, then rotate again, by just multiplying a few of these matrices together. It's an incredible computational shortcut.
Okay, let's try crossing that kinematics bridge, but we'll take the easy way first. If I give you all the robot's joint angles, how do we find the exact position and orientation of its tool? Well, this is forward kinematics.
And this is what makes it so easy. It's totally deterministic. Think of it like a function in math. You give it a set of inputs, the joint positions, and it gives you back exactly one answer for where the tool is. There's no ambiguity, no guesswork, just one right answer.
So how does it work? Well, it's kind of like you're walking down the robot's arm, one piece at a time. You start at the base, where you know exactly where you are. Then you use that first 4x4 matrix to calculate the position of the next link. Then you multiply by the next joint's matrix, and then the next, accumulating the whole chain of movements until you get to the very end. That final matrix tells you everything you need to know about where that tool is.
Great, so we can find the tool, but that's not actually that useful, is it? The real job is telling the tool where we want it to go, and having the robot figure out how to get there. And for that, we have to cross the hard side of the bridge. Welcome to the challenge of inverse kinematics.
So why is this so tough? Well, for a few big reasons. First, there might be multiple ways to reach the same target. Think about touching your nose. You can do it with your elbow pointing up or with your elbow pointing down. Two different solutions for the same goal. Second, there might be no solution at all if you're trying to reach something too far away. And finally, the math itself is just plain nasty. It's full of nonlinear equations that are really hard to solve. This is why IK is one of the most famous and heavily studied problems in all of robotics. To solve this mess, roboticists have two main tools in their toolbox. For some simpler robots, you can actually derive an exact, lightning-fast formula. That's an analytical solution. But for most complex robots, we have to use a numerical approach, which is basically a really smart way of guessing, checking how wrong you are, and then making a better guess over and over until you're close enough. It's that classic engineering trade-off. Do you want a perfect, fast solution that only works for one thing, or a slower one that can work for anything? Okay, so we figured out how to get the robot to a specific spot. But what about controlling its speed? What about making sure it moves smoothly along a path, like when it's welding a seam on a car? For that, we need a new, even more powerful tool, the Jacobian Matrix.
Don't let the name scare you. If forward kinematics is our position map, the Jacobian is our velocity map. It's a matrix that creates a direct link between the speeds of all the individual joints and the final speed of the tool out in the real world. This is, without a doubt, one of the most important tools in robot control. It's essential for pretty much anything that needs smooth, controlled motion.
And the structure of the Jacobian is just beautiful. It's a matrix that has 6 rows, and it has one column for every joint in the robot. The top 3 rows connect the joint speeds to the tool's linear speed, how fast it's moving along X, Y, and Z. The bottom 3 rows do the exact same thing for its rotational speed. So basically, each column tells you exactly how much that one joint is contributing to the tool's overall velocity. It's brilliant. And here's the really slick part. You'd think building this crazy velocity map would require some insane calculus, right? Nope. We can actually build the whole thing using pretty simple geometry. We just leverage what we already know from our forward kinematics to figure out how each joint's motion is going to affect the final velocity of the tool.
So we have maps for position, we have maps for velocity. We should be all set, right? Well, not quite. Turns out there are certain poses, certain configurations where all of our beautiful maps just fall apart. These are dangerous zones that every robot programmer has to learn to steer clear of.
It's called a kinematic singularity, and the easiest way to feel one is to do it yourself. Just stretch your arm all the way out, perfectly straight. From that position, you literally cannot move your hand any further away from your shoulder. No matter how you try to move your elbow, you've lost the ability to move in that direction. You've lost a degree of freedom. Your arm is in a singularity.
And the consequences for a robot are really, really bad. Not only can it get physically stuck, but the math trying to get it unstuck can go haywire and command the joints to move at literally infinite speeds. This can cause the robot to crash or shake violently or just shut down. That's why smart path planning isn't just about getting from point A to point B. It's about finding a path that actively avoids these mathematical traps. And what's so amazing, when you really step back and look at it, is that all of these ideas, position, velocity, even these dangerous dead ends, they all stem from one single, powerful, elegant framework, the kinematic chain. It is the core concept that makes all of modern robotics possible. Which, of course, leaves us with one final big question. Knowing where these traps are is one thing, but how can we design smarter algorithms that automatically plan complex, winding paths that are guaranteed to be safe and efficient from the start? Well, that challenge, that's what takes us to the next level of robotics, advanced motion planning. Thanks for watching.